Okay, thank you, Mr. Chairman, and thank you very much to the American Angus Association for inviting me here to speak today to such a great crowd. So what I'm going to do today is spend a little bit of time on where genomics is at right at the moment, and then most of the talk will be devoted to where genomics is going to in the future. So the last 10 years really have been a very exciting time to work in genetics because the technology we've developed to the point where you can take a tail hair sample or an ear punch from your animals, extract the DNA out of that sample, run it across one of these SNP chips, and then get back what we call genomic estimated breeding values or genomic enhanced estimated progeny differences for many different traits that we're interested in for beef breeding. And this technology is now very widely used in breeding decisions. There have been more than 3.5 million cattle genotyped with the technology around the world, and that includes both beef and dairy cattle. So now that we have such large numbers genotyped, I think it's good to look at the impact that that has had. So in 2016, can we see the impact? Now, the genomics technology is so powerful because you can get back these genomic estimated breeding values almost at the birth of the animal. As soon as you can pull a tail hair or get an ear punch to get that DNA from, you can get back these genomic breeding values and start to make selection decisions about that animal. So what we should see is that the generation interval, the age of breeding of the animals, is starting to come down, and that's leading to more rapid genetic gains. We're turning over the generations more rapidly. So are we actually seeing that? And the example I'll use is from the US dairy industry, where the technology's probably been running the longest, but you could equally look at Angus breeding as well, I think. So, do we see this reduction in generation interval? And this is for a paper that was very recently published using the US Holstein database. And what you see here is the generation interval, if we go from right to left, cows to breed cows, so these are cows in the herd leaving behind cows, dams to breed bulls, so these are the elite dams that are breeding the next generation of sires, sires to breed cows, so these are the bulls you use in your herd, and the really interesting one is the sires to breed the sires. This is the really pointy end of genetics. This is the sires of sons, the really elite bulls that are breeding the next crop of bulls. And what you can see if you look from 2007, which are the blue bars pre-genomics, to the orange bars, which is 2016, for all those different classes, there's been a drop in the generation interval. But where it's really substantial is these sires to breed sons. These real legends of the breed that leave behind lots of bulls that then go on to have an impact. And the generation interval there has reduced from 7 years, and that reflects the fact that progeny testing was previously required to identify these animals, down to 2 years. And the genomic breeding values are so accurate now that these really elite bulls can be identified very early. So the generation interval has really shrunk down for that class of animal. So what's the impact been on genetic gain? So this is an example of daughter fertility rate. And this was, as some of you will know, a real problem in the dairy industry a few years ago. There's been a lot of selection pressure put on to increase fertility. And what you can see is that for all the classes there, what we have here is the offspring year of birth on the x-axis and the daughter pregnancy rate on the y-axis. So for all the different classes, the pregnancy rate is going up. But where you see the most dramatic increase is the sires to breed bulls, that SB class there. And that again is the really pointy end of genetics. So we're getting, or they're observing, quite large increases in genetic gain for fertility. And that's quite pleasing because that's one of the harder traits to select for. So this just demonstrates that genomics is really having an impact on genetic gain. The question is, where do we go next with this technology? What else can we do with this technology? So I'm going to go through three possibilities. One is adding value to breeding decisions. The second is starting to use genomics as a management tool, and then finish on something that is in the future but does look rather exciting, which is rumen microbiome screening. So adding value to breeding decisions. When you pull that tail hair or do that ear punch and send away your dollars to get the animal genotyped, you really want to get back as much value as possible from that genotype. So what can we do to improve the value of the genotype? One way of improving the value of the genotype is to add in new traits that add to profitability. And genomics in beef cattle, particularly in Angus cattle, has already done this to some extent. Traits that were previously quite hard to get a hold on, like meat quality, marbling, fertility, and feed efficiency, there's now genomic breeding values for those traits, which means you can go out to any animal, any Angus animal, and get a genomic breeding value back on these traits. But we can also think of other traits that we could add in that you can get back from this genotype. And one that we're quite interested in Australia is heat tolerance. Heat stress has quite an impact on our animals. First of all, if there is a heat stress event, what you see is reduction in feed intake, reduction in growth rates. If it's a lactating cow, the amount of milk produced goes down quite a bit, and you can even get lactation stopping if there's enough heat stress. Heat stress also has a major impact on fertility, as anyone who's ever tried to mate cows during a heat event will know very well. Heat stress also increases susceptibility to disease and parasites. So what we'd like to do is improve the heat tolerance of our animals, particularly in those areas where heat events are quite common. And the Angus breed in Australia is quite interested in pushing Angus animals further north in Australia, up to the parts of the country where there is quite severe heat stress. So breeding for heat tolerance is quite interesting there. The next question is, if you do want to breed for this, do want to develop a genomic breeding value so you can select more heat-tolerant animals, how are you going to do this? What trait, what measurement are you actually going to use? So what I'll show you now is what we did in dairy cattle. So what we did in dairy cattle was combine two very large data sets to come up with our genomic breeding values for heat tolerance. And those large data sets were the herd recording information, how much milk cows were producing each day in the dairies, and the Bureau of Meteorology data. So we looked up for each herd in the data set the weather station that was closest to the herd and downloaded the temperature and humidity on the days the cows were milked. You actually end up with very large data sets when you do this. But we've combined this data to come up with a trait, a phenotype, that looks like this. So what you see when you put that data together is the temperature and humidity can increase. It doesn't affect production until you hit a threshold where the animal becomes heat stressed, and then the milk production really drops off. So on the x-axis there is a temperature-humidity index, combines temperature and humidity. On the y-axis is the milk production coming from the cows. If you wanted to think of a beef analogy, you could think of growth rate of the animals being impacted by heat stress. And I've got two example cows here. One is cow A in the blue, and she is affected by heat stress when it hits this threshold, but her production doesn't drop off as much as cow B. So we can say cow A there is tolerating heat stress better than cow B. This trait's actually heritable. There's genetic variation for the impact of heat stress on production. So we can breed for it, and we can come up with genomic breeding values for this trait. The size of the data set, we had a large number of herds in the study, about 1,700 Holstein herds and 500 Jersey herds, and altogether about 400,000 cows. And that's 400,000 cows where we could get this trait of how quickly their production is affected by heat stress, or how much it's affected. We also genotyped many of the sires of these cows. So now we're in a position to derive genomic breeding values for these animals. We have the trait measured, we have the same animals genotyped, we can come up with genomic breeding values for this new trait, heat tolerance. Now, a trick with genomic breeding values is always when you come up with a new trait, quite rightly, the industry asks the scientists to validate the trait. Show me that this trait really works in practice. And you should do this for all genomic breeding values. And I'll show you how we did this for, in this case, our dairy industry. So we have these genomic breeding values. How do we demonstrate you can really use them to breed for more heat-tolerant animals? So we did this validation study. We went out and we screened 400 heifers, and these were just heifers off fairly random farms, actually. And out of those 400 heifers, on our genomic breeding values, we identified the 24 that should be most heat-tolerant and 24 that should be worst affected by heat stress, the most heat-susceptible. And this selection was purely on their DNA, purely on their genomic breeding values. Then we were fortunate enough to have on our research station these climate control chambers that you can see. And in these chambers, we can control temperature and humidity, so we can run the animals through a mild heat stress event. It was relatively mild. And it was a 4-day event. So what we're looking for here is we've predicted these two groups of animals. One should be heat tolerant, one should be heat susceptible. What we're looking for is in those heat tolerant animals, the milk production doesn't drop off as badly as in the heat susceptible animals. So what do we see? And it turns out the genomic breeding values really did pull apart the two groups quite well. So here you see days 1, 2, 3 and 4 of the heat event, and on the y-axis you see the decline in milk production from the baseline. So this is from about 20 litres per milking. Day 1, nothing much happens, but by day 2, the heat susceptible animals, their production is really starting to drop off. Whereas the animals we said would be heat tolerant, their production isn't dropping off nearly as much. And it's the same for days 2 and 3. Also, quite pleasingly, we measured the core temperature of these animals, and the core temperature of the heat-tolerant animals was about 0.5 degrees lower than the heat-susceptible animals. So it really is starting to identify these heat-tolerant animals. And now that we've validated this trait, we've demonstrated fairly convincingly that it works it's going to be released as a new genomic breeding value for the Australian dairy industry. It was very good that the validation study worked. It's also a nice example of developing a new trait using large data sets from different sources. In this case, from the Bureau of Meteorology and from the herd recording data. And I think this is a bit of a trend for the future. The cropping industry has actually been very good at this recently. And I think in beef production, we can start to think about what big data sets are out there that we can combine with the data that we record to generate these new traits. Okay, so that's one source of value you can add to your genotype is the new traits. Another source of information you can give back is genomic mating plans. So this is to avoid inbreeding. To avoid inbreeding so you don't get the declines in fertility and production associated with inbreeding, and also to avoid recessive defects, some of which are lethal. So you can use the genomic information to do this. And to show this, I'll take you through a case study that we did. This was with one of our really leading Holstein breeders, and they wanted us to demonstrate, they genotyped all their heifers in their herd. They wanted us to demonstrate they could use this information to avoid inbreeding. So it's 49 heifers, and the question they had is which bulls should they choose, in this case for AI, out there, and which matings to make to maximise genetic gain and to reduce inbreeding. Just to show you the power of this information, in those 49 heifers, they had 3 full sisters from an ET program. So if you were only working with pedigree information, the relationship you would estimate between these 3 sisters would be exactly the same. If they're 3 full sisters, they should share, they're expected to share 50% of their genome. If you have a full brother or sister, you're expected to share 50% of your genome. But of course, you don't share 50% of your genome with your full brothers and sisters. Because of the chromosomes that you inherit from your mother and father, you can share more or less than that 50%. So when we genotype these heifers and we work out from the DNA information what proportion of their genome they share, we see something like this. So heifer 1 and 2 share 51% of their genome. So more than the expectation. Whereas heifers 1 and 3, they're less inbred to each other. They share 44% of their genome. So if you wanted to select 2 heifers to keep in the herd to reduce future inbreeding, you take heifer 1 and 3. Just incidentally, if you look at that picture of those heifers, you might think it's the 2 heifers on the right that share most of their genome because they look most similar. But coat colour is always a bit deceiving. It's actually the heifer on the far right and far left that share most of their genome. Okay, so to take this a bit further, we can come up with genomic mating plans for these heifers. So what we have here is a graph where we have 49 rows going down, and each row is a heifer. And each column is a possible sire that this breeder wanted to use. And each dot there, or each square, is the degree of relationship based on the genotype data that these animals share. And the more red it is, the more they're related, and the less you want to make that mating. So red is bad. Red says you don't want to make this mating because you're going to end up with an inbred progeny. If you compare what you get from pedigree and the genomics, they look quite similar. The red dots are mostly in the same places, but there's certainly places where the genomics picks up a bad mating, a mating where if you mate those 2 animals, they're highly related, you're going to get an inbred progeny. And that's because the genomic information really traces the pedigree all the way back to the founding animals, whereas the pedigree itself can have some holes in it. And we were able to demonstrate to this breeder that they could make matings, they could choose matings using a program we gave them, computer program, where they ended up with 1.5% less inbreeding for the same genetic merit. So it shows you there's power in this genomic information to decrease inbreeding without really decreasing merit. So there are two possibilities for adding value to breeding decisions. There's more, but what I'll move on to next is using genomic information for management decisions. And the topic I'll touch on here is feedlot pre-screening. So the idea here is there's differences in profitability of the animals that go through the feedlot. Some animals are very profitable, they hit high marbling scores, they're very feed efficient, they don't get disease, whereas other animals actually cost a lot of money to put through the feedlot. They don't hit the marbling scores without an awful lot of feeding, they're not feed efficient, they get diseased, and so on. So you could actually use the genomic breeding values or the genomic enhanced estimated progeny differences to screen animals before they go into feedlot based on how profitable those animals will be. This idea has actually been around for quite a while, but the thing that stopped it happening is the cost of genotyping. But the genotyping cost is now coming down to a point where it's almost practical to do. However, for the last topic that I want to touch on, if you genotype those animals, you're only getting a handle on the contribution to profit through the feedlot from the animal's own genome. And every animal actually carries tens of millions, hundreds of millions, if not a billion, other genomes along with it. And that is the microbes that are in the rumen of our animals. And they also contribute to feed efficiency and possibly disease resistance as well. So this is just a magazine where they were talking about articles that had discovered that human gut flora had quite a big influence on disease status, metabolic diseases, and so on in people. But if microbes maketh a man, even more so they maketh the cow. Now, a few years ago, there was just no possibility of getting a handle on the rumen microbiome, the rumen microbes. What was in there, how abundant each type of bacteria and so on was. But the sequencing technology, which has been developed for human medical genetics really, but translated across to livestock, it's now at a point where you can take a handful of rumen contents, extract the DNA out of those rumen contents, and profile the rumens of the animals. So you can get an idea of what bugs are in there, what bacteria, archaea, and so on are in there, and their relative abundance. And you can get a profile of this for each animal. And the work we've done and others have done has shown that every animal carries a subtly different rumen microbe profile. And the question is, does this have any association to traits that we're interested in, like feed efficiency, for example? So this is really something for the future. We're just starting to do experiments where we tie up the rumen microbe profile with feed efficiency, but I'll show you some very preliminary results. And this is from a very small data set, so certainly much bigger studies need to be done, but I'll show you these very preliminary results. So in this experiment, we had 28 heifers measured for feed efficiency using these individual feeding bins that you can see here. We also took rumen contents from each of these animals and profiled their rumen microbiome. So we got the abundance and composition of the bugs in their rumen. The question we asked ourselves was, from that rumen profile, how accurately could we predict feed efficiency? And the real question is, if you take the rumen genomics, so the rumen profile, plus the feed efficiency genomic breeding value, so the cow's own genetics for feed efficiency, add them together, do you improve the prediction for feed efficiency? Do you get a more accurate prediction? And if you do, then you could use that as a good screening tool in the future. So this is just results of this admittedly very small study, just to show you what the results look like. So from the rumen microbiome, this is looking at the differences in the abundance of these different bugs and the composition of the bugs. We were able to predict feed efficiency with an accuracy of 0.49. That means we're getting that's the correlation with feed efficiency. It means we're getting a fairly good prediction, certainly not perfect, but fairly good, from just the composition and abundance of those bugs. It does have a very wide confidence interval, reflecting again that it's a small study. If you do the genomic prediction, so this is based on our feed efficiency genomic breeding value for dairy cattle, it's a little bit lower than that, it's 0.33. But when you combine them together, at least in this small study, we got an increase in how accurately we could predict feed efficiency. Again, small study, definitely needs to be repeated in a larger group, but at least it gives us a future direction. It says if we could get a handle on this rumen microbial profile, add that to the cow's own genomics through our genomic breeding value, we might have something that could really pull apart those animals that are feed efficient and those that aren't. Okay, so to finish up, genomic selection, genomic breeding values are now pretty widely used in cattle to improve genetic gain. And I think one point to make is we're getting more balanced genetic gain. Because genomic, you can get reasonably accurate genomic breeding values for fertility, health traits and so on, it brings those traits up to a level where production has been. So you can get a more balanced genetic gain from doing that. There's the opportunity to select for new traits that might contribute to profit, and heat tolerance was the example I used. And you can also use the information to run genomic mating plans to avoid inbreeding. And that's going to be more and more important in the future. We're just starting to shift into a space, I think, where the genomic information is going to be useful for management of the animals. It's just starting to happen. The price point probably needs to come down a little bit to make that a real goer, but certainly the technology's nearly there. And that's particularly if we start to combine the cow's own or the animal's own genomics with the genomics of all the microbes that the animal carries as well to predict performance. Okay, just finally, I would like to thank a few people that have really contributed a lot to this work. Josie Gardner, who ran the heat tolerance experiment. It's quite a big experiment to run. And also Min Wang, who did the microbiome predictions that you saw there. So thank you very much.